Dear friends, this is my tutorial 48-1. So in this tutorial I'm going to teach you how to calculate Fukui functions, especially for radical attack using Gaussian and one more software, UCA-FUKUI. This is the software we are going to use to calculate the Fukui functions. So first we will optimize our system using Gaussian. So this is the things. So now we will see that input files for the geometry optimization and followed by the UCA-FUKUI function calculations. So this is the DCF molecule, that is diclofenac. So I'm going to calculate for radical attack site for this DCF molecule. So just I will show you that input files for that DCF molecule. So I will also open with Gauss view and I will show you. So first I will double click and open with the Notepad++. So this is the preparation method for in geometry optimization input file. So first what you have to do, you have to mention %chk equal to dcf.chk. This is the name of the molecule. You can also write diclofenac. Just I will mention the short form DCF. Then you have to mention the memory 1 GB. So N4 shared, I have used 4 shared memory processor for this one. Course this is actually. So then you have to mention this hashtag and the B3LP and a 6311 G double star and opt frequency. So in this molecule I used only one basis set. That's why I mentioned here itself. If I am using different kind of basis set, I will mention bottom of the input file. So then you have to give one space, then you have to mention DCF, name of the system, then a space, then you have to mention the charge. Total charge of the DCF molecule is 0. Then you have to mention the spin multiplicity is 1. So this is the Cartesian coordinate of that molecule. So this is the total 30 atom is there. Then finally what you have to do, just you can keep your cursor and keep enter. Then only you will get some space. Then only that software detect that file input file entered. So for that you have to do always, otherwise we'll get some error. Then you can save it and submit it to your Windows version of Gaussian file. You will get optimized within 1 or 2 hours. So if you want to use a Linux version, so this may change according to your Linux version. This is the memory will change, N4 shared also will change. So that's all. Then if you are using Linux version, you need to change dcf.com file format. Then only Linux calculation will run. So this is the .ggf is Windows calculation. So that's all. Now I will open with Gauss view and show you that input file. So just click your Gauss view. So just drag. Drag into here, it will show. This is the diclofenac molecule for geometry optimization. So I already completed that geometry optimization. I will show you that output file. So I will open with Notepad++. So this is the completed DCF file log file. So you can see here what we mentioned in that file. So what we mentioned in the input file, everything will printed here. So this is the theory. So this is a basis set used for this calculation. So this is the Cartesian coordinate of this molecule. So here you can see charge is 0, spin multiplicity is 1. So like that you will get. So if you go down, so first the optimization will complete. So I will show you that page. After that frequency calculation will run. So this is the, you will get one paragraph numbers. So this is the completion of your geometry optimization. So now your calculation will complete from here. Then the calculation, the system will take optimized coordinate to do the frequency calculation. You can see here frequency calculation will run. So then we can also go down. you can see the normal termination of Gaussian 16 calculation. So our calculation, geometry calculation completed without any error. So now we will do our NBO calculation in order to get the Fukui functions for radical attack, and also the electrophilic attack, nucleophilic attack also we will get. So I will make a different video for the nucleophilic attack and electrophilic attack. So mainly we will see in this video radical attack. So you can also view this file using Gauss view. Just you can drag into Gauss view. So go to result file, you can see summary also, you can see this is the summary of that our calculation. So this is the total energy. There is no imaginary frequency, that means without any negative frequency our system get optimized. So if you are getting negative frequency, you have to do re-optimize again and again in order to get that 0. So this is the basis set we use, is mentioned here. The spin multiplicity is singlet. So this is the things. So if you want to see that vibrational frequency, just go to here, result, click vibration. You will see this small box. You can see this the vibrational frequency. Here you can see that green colored one. Just click it, it will show start vibration. So you can click here. Just you can using down arrow of your computer, just you can go by down one by one, it will show the frequency of corresponding bond. So that's all. So now we can stop animation and close this. So next we are going to do the NBO calculation for Fukui function analysis. So for that, what you have to do, just go after dragging geometry optimization completed, you can open with your Gauss view, and now you can save this optimized coordinate for NBO calculation. Just you can go to this file. Here you can see save. Save means it will save that optimized coordinate for further calculation. So here you can change rename it, just mention new, so it will save into that folder. So I will show you that optimized coordinate. So now this is the optimized Cartesian coordinate for NBO calculation. So I will open this. So we have to use this Cartesian coordinate for our NBO calculations in order to get the Fukui function. So we should not use the initial Cartesian coordinate what we submitted for geometry optimization. So be careful with this. So now we will do the NBO calculation. So this is the NBO calculation folder. So actually I did early every calculations in order to get the Fukui function. So first what you have to do, we have to do the NBO calculation for neutral molecule. Already we optimized in the neutral form only. So this is the NBO N0 means neutral. So I will show you that input file. So see, so this is the NBO calculation input file. So everything is same, just you can mention your DCF underscore NBO. So this I did with my laptop, that's why I mentioned 6 million watts MW. So NPro shade also I used 2 for this calculation. So that's the theory and basis set same, you should have used same. This that you have to mention pop equal to NBO. So you have to write this pop equal to NBO in order to get your NBO calculation. Then you have to mention that space, then you have to mention DCF underscore NBO. So here what you are going to do, we are going to use NBO orbital in order to get the Fukui functions. So now you have to give space, then you have to mention 0, then you have to mention 1. So this is actually optimized Cartesian coordinate what we saved from that geometry optimization output file. So you have to copy paste here. So already I did everything. So this is I prepared the input file. So finally you have to give some space, then we can save and submit it. Your calculation will complete it within 20 minutes. So this is the output file. So here you will get your charge. This is the NBO charge. So natural atomic orbital, natural bond orbital analysis, like that you will get NBO version 3.1. So here we will get our charge, natural charges of our system. So that Fukui UCA-FUKUI function will so what is this? So UCA-FUKUI will use this natural charges in order to get our Fukui function. So we have to do first neutral molecule pop equal to NBO calculation. So then what you have to do, so just then we have to do two more calculation, that is n minus 1, n plus 1. So n plus 1 means we are going to add one electron to the system. That means we are going to change charges is minus 1. So that is the anionic one. So this is the input file for anionic. So you have to use the same Cartesian coordinate for this calculation also. You do not optimize the system. Okay, just you can change into the charge of that one, and spin multiplicity just you will do the single point calculation. That's all. No need to do geometry optimization. So here I mentioned DCF NBO n plus 1. N plus 1 means we are adding one electron to the system. So for to know that we are mentioning like this. Then you have to mention memory, n pro-shared, theory and a basis set, pop equal to NBO, then space, then this name of the system, then space, then you have to mention minus 1. We are added one electron to the system. This is the anionic one. So then you have to change the according to spin multiplicity into 2. So if we mention 1, it won't run. So we have to mention 2 spin multiples for this kind of calculation. So that's all. This is the optimized Cartesian coordinate what we used to for a neutral form. So then you have to give some spaces, then you can save it. So you can submit this calculation. This calculation also will finish within 10 to 20 minutes. So likewise you have to do one more calculation, that is NBO n minus 1. So this is the NBO n minus 1 fold. That means we are removing one electron from the system. N minus 1 means, so I will show you that output file. So this is I will show you the input file. So this is the input file for n minus 1. N minus 1 means we are removing one electron from the system. So this is the DCF NBO n minus 1 CHK. This is the 6 million memory, and this is the n pro shared memory. So then you have to mention theory and basis set and pop equal to NBO. Then you have to change according to there is a neutral form, means cationic form this is. So you have to mention plus 1. So 1 we have mentioned, spin multiplicity 2. So then we have to do just a single point energy calculation in order to get that NBO charges. So you have to submit this NBO neutral form, NBO anionic form and NBO cationic form. So you have to submit this calculation. You can get your CHK file also. You can get your output file. So I will show you that folder. What are the so now I did all 3 calculation. I have all 3 output file. This is the neutral form output file. So this is the anionic form output file. So this is cationic form output file. So we need 3 output file in order to get our Fukui functions for radical attack. So this is the things. Now we can use that software in order to get our Fukui functions. So this is the important things. Just you take that optimized Cartesian coordinate, do these 3 single point energy calculation. So one is neutral form, so another one is that anionic form, another one is cationic form. So you can do these 3 calculation, keep it one folder. So now we can analyze our Fukui function. This is a very important thing. So I will open that UCA. So this is the UCA-FUKUI version 2. Just to double click, so it will open like this. So now what you have to do, you have to again press this one, then only it will open. So if you want to see tutorial, you can see, otherwise you can skip. So this is the our UCA-FUKUI version 2.1 software. So we are going to use this software in order to get our Fukui functions for radical attack and also electrophilic and nucleophilic attack sites. So now we will start calculate our things. So here you can see atomic reactivity indices. This is the one we are going to do. Just you can, if you click this one, it will show different kind of things. So we are going to use finite difference approximation. So if you keep your mouse cursor on this, means it will show this kind of things. So here you can see different kind of things is there. So here what we are going to use, so this one based on natural population atomic analysis, that means NBO analysis. Just we have to click, so it will open small page like this. So now we are going to add our input files. So here you can see, go to file, and so first you can see open neutral population from logout file. So we are going to use, first one is log neutral log file of this NBO calculation. Just you can click, so it will, you can go to corresponding your folder. So this is the diclofenac. So this is the DCF molecule. Actually this is the neutral one. So our file is here, so I will go there. So these are our files. So we have neutral one, anionic, cationic. First we have to open our neutral one. So this is the neutral NBO output file. Open it. So it will come that it will extract that NPA charges from that output file, NBO charges. So second one is we have to open anion population from logout file. It means n plus 1. We are going to open n plus 1. This means anion. Just you can open, so it will extract that one. So actually here alpha beta electron will be there. So that software itself it combine two different kind of that alpha beta electrons, make it one. So then we have to open cationic one. So this is the cationic one, that means one electron removed, one, n minus 1. Just you can open it. So that's all. So we have loaded that 3 output files. This is an NPA neutral, NPA anion, NPA cation. Here also the two kind of electron is there, alpha beta electron. The system will calculate and combine with these two electrons and make it one. So you don't need to do manually. So that's all. This is the important things. Then what you have to do, you have to calculate. So here you can see F minus. F minus means electrophilic attack. So first we will calculate F minus Fukui index. If you click that one, it will come here, F minus Fukui index. So second one means nucleophilic attack, F plus. So if you click F plus, it will come F plus Fukui index. Then we have to calculate that F0. This is the radical attack. So what you have to do, again go to calculate and you can click F0 Fukui index. So now we will get that our radical attack site. So now what we have to do, if you want that all condensed Fukui function, just you can click it. So it will give the dual descriptor. So this is the NPA charges of 3 system, Fukui functions of this system, means this that F minus, F plus and F0. This that electrophilic site, this is the nucleophilic site, this is the radical site. So now what you have to do, we have to copy these things into the Excel sheet, and you can use it for your research purpose. So I will show you how to calculate, how to take these Fukui functions. So just you can select all this is control A. I think control A not working. Just what you have to do, just you can select all. So then you have to do, just you can copy. So open a new Excel sheet. Sure, Excel sheet, just you can paste it here. So this is F minus, just you can mention F minus. So we need 2 columns, just I left. So here you can mention F minus. F minus electrophilic site. So then F plus and F0. So now we have to take F. Okay, then you can copy and paste it. Again you can also copy this radical attack site. So that atom number, just you can open any input files for your NBO calculation. So just you can use Alt and select mouse left side. So Control C, you can paste it here. So this atom will paste all the atom, 30 atom. So atom, here you can mention site name, means number. So if you want to know, this is the atom. So here what you have to do, you can just to type 1 2 3 4 5 6 7 8 1 28 29 30. Total 30 atom is there. So now I will we will find that radical site for radical attack sites. So we should know the site. So for what we have to do, just we can open our input files, any input file. Just we want to know the numbers, which atom. Just open any input or output file. So this is the thing. So now we can see that sites. So here you can see different kind of carbon atom is there. So which carbon atom is more feasible for radical attack, we have to find that one. So here you can see F0. You see that the C19 you can see. So just you can make a highlight C. So if you compare with all atoms, so this C19 atom possesses the higher value. So that indicate that, so this C19 atom is more feasible for this radical attack. So I will show you that radical attack site in that this molecule file. So actually, so if you keep, this is the C19 atom, so this atom only more feasible for radical attacking site. So we can see the second one also, second feasible site. So if you go, you can see nitrogen also possess 0.0998. so if you come, I think the second is nitrogen only. So the second possible site is nitrogen. So we can also find third also. You can see somewhere any higher values there are not. So this chlorine atom also possess somewhat more only. So this also is feasible for radical attacks. So it's around 0.0669 is there. And one more atom also is there. I will show you this one. So this atoms C12, we can also check C12. So this C12 also more possible for radical attack. So likewise you have to compare your find your radical attacking site, so for your Fukui from your Fukui function calculations. So if you want to make this one in, so copy this one, you can also paste it to your Word document. Just open your new Word document. Just you can paste it, you will get everything. So just you can arrange based on your requirement. So that's all. This is the Fukui function calculation for radical attack. So if you like my video, please like, subscribe, comment and share to your friends. Thank you for watching. Enjoy.